Good evening. Today we will study the one of the last two major theorems in this class. So the last two lessons traditionally in Calculus 3 are devoted to studying the two major theorems in calculus, namely the Stoke's theorem and the divergence theorem. So we're going to cover this in two separate lectures. We're not going to spend an awful amount of time. In general, these topics are not strictly mandatory, and because the amount of material covered in Calculus 3 is so much, it is often the case that we don't have time to do it in the classroom, which is a shame actually, because not only they are interesting theorems, but they are very useful to review all the concepts, or not all, but many concepts that we learn already. So going over a problem involving these theorems, it's a very good opportunity to practice some of the concepts you learned in the last chapter, or in the class in general, which works very well as a review for the final exam, for example. Hopefully, I managed to cover it most of the time. There are exceptions depending on the pace that we had during the semester. So hopefully at the time of this recording for the class that I'm teaching right now, it's likely that we're going to go over these two theorems. So let's start with the Stoke's theorem. We can describe it very easily based on what we learned before. This is nothing but a three-dimensional version of Green's theorem. Let me remind you briefly what the Green's theorem states. I'm going to put it here in the corner because I want to leave most of the room for the Stoke's theorem, obviously. So remember, if you have a vector field in the plane in a simply connected domain enclosed by a closed curve, so if you have, if f is given by just two components p and q, then and the curve is oriented counterclockwise, then the line integral over the curve of p dx plus q dy is the double integral over the domain enclosed by the curve of dq dx minus dp dy, which is actually the curl of the vector field in the plane. Right, so remember, this is nothing but the curl of the vector field, or basically remember, it states that the amount of the circulation of the vector field around the curve is equal to the sum, if you want, in the limit of microcirculations inside the curve. If you imagine that this vector field is broken down into so-called microcirculations. So if you remember that analogy we had with fluid dynamics when we covered the Green's theorem. So Stoke's theorem is essentially the three-dimensional versions. What does that mean? Well, it means that the curve now is a 3D curve. So let's imagine, for example, that you have this type of, twisted around curve with in 3D. And suppose that, let me see how I can do that. So let's say this is like that. And you know what, let me actually do it, let me do another picture here. Okay, so suppose you have this curve in 3D, which is again closed, but it's not necessarily situated in a plane. And suppose this curve encloses or surrounds a surface. So this surface, I'm going to represent it here like that with these lines, kind of like a hat. Let's put it this way. Okay, so this is like a hat, right? So a closed curve that surrounds a surface. Okay, so just like in 3D, we're going to relate the integral. Stoke's theorem relates the integral of along the curve, the line integral, with this time not a double integral, but the equivalent of it for generic surfaces, namely a surface integral. So let's say S is the surface. So S is the surface enclosed by C. And the Stoke's theorem states that, let's write it here with a different color, states that the line integral on this curve over a vector field. So suppose again you have a vector field in 3D. So the line integral of this vector field, sometimes again you can add this little symbol here to indicate that this is a closed curve, is equal to the surface integral of the curl of the vector field along the normal oriented, I'll tell you in a minute how we oriented it in, right? So ds. So this theorem is true, and the orientation, so that we make sure the sign is correct, the orientation is such a way that the normal follows the right-hand rule the way you actually traverse the curve. So let me actually explain this a little bit in more details. Because you know this is in 3D, right? So this curve could be tilted upside down and whatever, right? It can be in any position you want. So it doesn't make sense to talk about counterclockwise or clockwise. So to make a convention of oriented this curve, so that the theorem is consistent in any configuration, we're gonna orient the curve. So we're gonna orient both the curve and the surface such that it follows the right-hand rule, meaning that the fingers curl in the direction of the motion on the curve. So that the normal, you orient the surface so that the normal points in the direction of the thumb with the right hand. Another way of putting it, if you imagine yourself walking on the curve, you're going to basically keep the normal upward and to your left as you walk around the curve. So you pick basically a way of going over the curve, and in doing so, you're going to orient the surface such that you will see the normal to the surface always pointing upward from your perspective, of course, as you walk on the curve, and to your left. Or like I said, you follow the right-hand rule. You curl the fingers around the motion of the curve, and then the thumb will point in the direction of the normal. Okay, so it has obviously a physical meaning, this theorem. We talked about the connection with the fluid dynamics. When is it actually useful from a mathematical standpoint? And the answer is basically whether you do it via a line integral or via a surface integral of the curl, it depends on the function at hand. If you suspect that one way of doing it is going to be much easier, and often the difference could be quite dramatic in terms of how easy it can be if you switch from one side to another. Usually the curl, the surface integral could be easier, especially if, for example, by taking various derivatives of the vector field, you expect to make the function to integrate easier. So here is a classical example of the sort. So let's start with the first example. Let's say I have a vector field with the components given by x plus y squared, y plus z squared, z plus x squared. And I want to find the line integral where the curve is going to be the contour of the following triangle connecting. So C is going to be the triangle connecting the points let's see, 0, 0, 1, 0, 1, 0, and then 1, 0, 0. Okay, so my special ink actually just I need to change actually to replace the ink in the special pen. So I'm gonna just make a little break here. Stay tuned. All right, so let's continue. So like I said, the curve is a triangle given by these points. So let's sketch that triangle. So it has some sort of a symmetry, as you can see here, right? And let's say, as you look at this triangle from above, if you want, let's say the triangle is traversed counterclockwise. Okay. And if I want to use the Stokes theorem, eventually notice that as I walk on the triangle, the normal should point basically kind of upward like that. In order to use the Stokes theorem. Now, why would you want to use the Stokes theorem? So there are several ideas and several reasons why you might want to do that. Notice that to compute this as a line integral, you actually have to do 3 line integrals. Why? Because the path, the closed path, is made of 3 pieces. It's not going to be overly difficult, but you still have to break it down into 3 pieces because each piece has its own parameterization. So it's basically like solving 3 line integrals. Furthermore, I don't know how tedious these integrals are when the time comes to actually plug in the components of each curve into the vector field. Another clue that via Stokes theorem might be easier is to actually look at the curl. So actually let's compute this curl, or set it up for computing the curl. So remember that symbolic determinant with the partial operators. And then P is x plus y squared, y plus z squared, and z plus x squared. So remember, in the curl, each component, oops, I overlapped it with something that I wrote before. Sorry about that. Let me write it down one more time. I overlapped accidentally what I wrote before. So remember that when you compute the curl, each partial derivative is with respect to the opposite or to the other component. So for example, the partial derivative of the first component are always in terms of the second and the third variables. So for example, if I look at x plus y squared, I know already that partial z is going to be 0. And partial y is not going to be that bad, 2y, right? The middle one also will have some 0 because partial x of the middle component is 0 and so on. So I can expect that actually the curl would be relatively easier. Let's actually just compute it, because if I'm going to proceed with Stokes theorem, I'm going to integrate the curl, right? So one more time, just to not get confused. On the left is the integral of the vector field. On the right is the integral of the curl. By the way, we'll talk about that toward the end. These are called versions of the fundamental theorem of calculus because they express an integral in terms of the integral of a derivative. So just like the fundamental theorem of calculus states that the integral of a derivative is in terms of an antiderivative, in the same way you can think of big F as some sort of an antiderivative of the curl. To be honest with you, I mean, I know many books call these versions of the fundamental theorem of calculus. I mean, I don't know if it's really that much useful as an analogy, because, to say that curl F is a type of derivative of F, I think has some kind of confusing part related to it. Like, we have a very precise definition of what the derivative is, what a partial derivative is, what a directional derivative. I don't know if we can call a curl as another derivative. It's a quantity, it's a vector obtained via derivatives, but which represents something very specific, right? So the amount of circulation in the vector field, so the same thing as the divergence. But anyway, this is a minor digression. I mean, it's not that important. So let's compute this curl. So the first component will be dq dy. So this is pqr, so the r dy, so that's going to be 0 minus 2z, comma, the middle component of the curl, that's going to be 2x minus 0 with a sign change, so minus 2x, and the last component will be 0 minus 2y. So altogether the curl is minus 2z minus 2x and minus 2y. Okay. So like I said, we're going to do the line integral via Stoke's theorem. That means we're going to do instead the surface integral of the curl. So then how do I apply Stoke's theorem? So what is the surface enclosed by the closed curve? Remember that surface could be three-dimensional, although in this case the surface itself happens to be actually a flat shape, the interior of the triangle. So S is the interior of the triangle. We can still apply Stoke's theorem, it's still a surface in 3D, right? But just to point out, it doesn't have to be flat, as you will see in my next example. Okay, so then we're going to have to find the parametrization of that surface. So you need to find the equation of that plane. If it's not obvious, because of the symmetry, the equation of this plane, represented by this interior of the triangle, is going to be actually x plus y plus z equals 1. It's easy to see this because of this type of symmetry, I mean, with respect to the origin, right? So it's, the center is kind of equally distanced from those points, 1, 0, 0, 0, 1, 0, 0, 0, 1. But if it's not obvious, you'll have to come up with, of course, two vectors, compute the normal, and then find the equation of the plane. Okay, so what is an obvious parametrization of the surface as a parameter? We can pick u to be x, and v to be y, which means z is going to be 1 minus u minus v. And now let's be careful with the domain itself, because we work actually in the first quadrant. The domain, the parameter domain, is going to be the interior of the following triangle, right? Because 1 minus x minus y, or 1 minus u minus v, should be greater than 0, right? Because z is greater than 0. Okay, so therefore, if I were to sketch the parameter domain of the surface in v and u, this is it, right? So the interior of that triangle. Okay, so I think we have everything we need. Now let's set up the surface integral over the curl. So we're going to need, so let's write down, of course, the surface as a parametric surface. So that's going to be u, v, 1 minus u minus v. We're going to compute now partial u, which, of course, because it's all linear, this is going to be made of constants only. So 1, 0, negative 1. And rv would be 0, 1, negative 1 again. And then the cross product of the two, which we're going to need, right, in the surface integral, the cross product of the two will be, well, the normal is 1, 1, 1. You can also guess this, right? So it's going to be 1, 1, and 1. Okay, so now finally we compute the integral. So therefore the line integral, if this is the objective to begin with, via Stokes becomes the surface integral over of the curl dot n ds. And now this becomes a double integral over the parameter domain, u and v. And now it's time to substitute the vector field onto the surface. I mean, plug in the surface components on the vector field. So let's do that carefully. The vector field, again, to integrate is not f, just to keep in mind, right? Take a look at this, right? The vector field is the curl. So minus 2z becomes minus 2 quantity 1 minus u minus v, comma minus 2x, which is minus 2u, and then finally minus 2v, I mean minus 2y, which is actually minus 2v. And this is dot r, this is dot ru cross rv, which in my case is 1, 1, 1 dA. Okay, so now we're going to have to compute this double integral. Let's see what we get after we computed the cross product. So minus 2 plus 2u plus 2v times 1, minus 2u times 1, minus 2v times 1. 2u cancels out, 2v cancels out, and notice, I think I missed something, 1 second. No, I didn't miss anything, yeah. So notice that it's really easy compared to doing that line integral, because you basically, it boils down to actually integrating a constant. Now the setup still takes some time. Again, this is where you have to be careful, to go very carefully on the setup, right, to choose all the components. But the integral itself now becomes much easier to solve. So look at the parameter domain. We can treat it as a type 1 domain. So let's say I can take the integral in terms of u on the outside from 0 to 1. And then the bounds for v run from 0 to 1 minus u. Because the equation of that boundary on the domain is u plus v equals 1, right? So the inner bounds for v run from 0 to 1 minus u, negative 2 dv du. Okay, innermost integral is minus 2v, evaluated between 0 and 1 minus u. And that ends up being minus 2 plus 2u. Antiderivative is minus 2u plus u squared between 0 and 1. That's minus 2 plus 1 equals negative 1. Okay, so as it turns out, the overall circulation, if I move around that path, it's actually in the opposite direction of motion, right? That's one physical interpretation, because the overall integral ended up being negative. So in my next example, I want to do a problem both ways, both via line integral and surface integral, and then you decide which one feels easier. And that'll be sufficient for today's lesson. So stay tuned. All right, so in this example, let's verify the Stokes theorem, meaning that let's do both sides of the equality. Verify the Stokes theorem for the following problem. Suppose that S, the surface, S is the cone, z squared equals x squared plus y squared, z between 0 and 4, oriented downward from our perspective, if we look at it. And then the vector field to integrate f of x, y, z, let's say, is made of the components minus y, x, negative 2. All right, so let's sketch this a little bit. If z equals 4, notice that the top is going to be x squared plus y squared equals 16, which is a circle of radius 4 in the z equals 4 plane. Right, so let's actually sketch this cone here. It's going to be open upward. Like that. And then this is z equals 4, let's say, and this is basically the top. And then the surface, let's let me see if I can do it with kind of like faded color like that. The surface is this, and it is oriented downward, meaning that the normal is going to be like that, perpendicular to the cone, but pointing downward. Okay, so if I want to use the Stoke theorem to verify the Stoke theorem, what is the Stoke theorem? So first of all, we're going to have a relationship between the, so, what's the configuration for the Stokes theorem? I have to view this surface as enclosed by a curve. And the curve obviously is going to be the circle itself. So this is the curve that encloses or surrounds the surface S. Remember, this is the whole idea with Stoke's theorem. This theorem is in 3 dimensions. The surface doesn't have to be flat as long as it is surrounded by a closed curve. Okay, now using the right-hand rule, like I said, if you walk around the curve and you want to keep the normal upward and to your left, that means you have to actually walk clockwise as you see this curve from above. So if you curl around the fingers of your right hand, the thumb should point downward in the direction of the normal. So basically this is the motion on the curve. So let's keep that in mind. So this is C. And this is again S. So let's start by doing first the left side of the inequality. Let's compute the integral using a line integral. F dot TDS. So I need to actually come up with a parametrization for this curve, first of all, right? And then do the line integral. Now, if you look at it from above, the x and y follow the coordinates of a circle. The most logical parametrization that you can have for a curve like this is to use basically polar coordinates. But because you want to traverse this curve clockwise instead of counterclockwise, you want basically your parameterization to be the radius is 4 in this case, cosine of minus t. If you reverse the sign of, if t again runs between 0 and 2 pi, but instead you take the trigonometric function cosine and sine of minus t, this has the effect of actually going in the opposite clockwise rather than counterclockwise direction. So x and y have polar coordinates for cosine of minus t, sine of minus t, and the parameter domain obviously is 0 and 2 pi. And z is a constant because that circle is in the z equals 4 plane. So the curve, the parametrization of the curve, which is, remember the parametrization is not unique, but the most logical one that probably is going to be easier to deal with, is this one, right? So cosine of minus t is the same as cosine of t because it's an even function. And then 4 sine minus t is minus 4 sine of t. And then the z coordinate is 4. And again, the parameter domain is 0 and 2 pi. What else do we need? We need a parametrization. No, we need we're going to deal with the surface later on. That's all we need for the line integral, right? So now we can just proceed and compute the line integral. The vector field is over here, right? It's minus y x minus 2. So therefore the line integral of f dot TDS, which remember another notation is f dot dr, right? Is you dot the product with the vector field evaluated at the surface, at the curve. So basically 4 cosine will be x, minus 4 sine will be y, and z will be 4 into the vector field. So the vector field becomes minus y, which is actually 4 sine of t, and then x, which is 4 cosine of t. There's no z to plug in. The third component of the vector field is a constant. And then dot r prime of t, the derivative of r, which is minus 4 sine, minus 4 cosine of t, and 0. And so let's compute the dot product now. We get minus 16 sine squared of t, minus 16 cosine squared of t, and then plus 0. And it does look like probably this is going to be the easier way to go about it. We'll see what we get in by computing the curl first. And notice this is opposite from the previous example. In the previous example, computing the curl as a surface integral was easier. But in this case, again, we end up with a constant. Because you pull out minus 16, this sine square plus cosine square becomes 1. So you just integrate minus 16 with respect to t. That's minus 32 pi. So for example, if the question here was to ask how much of the flow goes across the surface, like for example, let's say this is a cup of water and you ask yourself, or a membrane in some vector fluid, and you ask yourself, how much fluid goes from the inside of the cup to the outside, the answer is not only it doesn't, in fact, there is an inflow, right? Because the value of the, sorry, I take that back. That was with the, scratch that. I was thinking in terms of the divergence theorem. I'm ahead of my my lesson. This is about the circulation, right? So the interpretation here is that the circulation around the curve is in the opposite direction of motion. So in fact, most of the vector field in this case circulate clockwise, right? That's the meaning of the fact that the integral circulate counterclockwise. That's the meaning of the fact that the integral in the clockwise direction was negative. So that means most of the fluid circulates in the opposite counterclockwise direction. All right, so moving on now to compute the same thing, and let's check to see if we get the same thing via a surface integral. So now I have to look at the cone as a surface and come up with a parametrization for it. So let's actually, for a change, because remember, there are parametrizations you can use in terms of polar coordinates as well. But let's actually use Cartesian coordinates, because remember, parametrization is not unique, so there's no way to know beforehand whether it's going to be easier or not. You may guess at some point, but it may take sometimes trial and error to figure out which parametrization is more useful. And it's possible you could do the same problem via multiple parametrizations, so that's also the case. So like I said, the equation of the cone is this, and let's choose kind of like the default parametrization in which x becomes u, y becomes v, and in this case of z is going to be square root of u squared plus v squared. Okay, yes, square root of u squared plus v squared, because it's positive, right? We look at z between 0 and 4. Okay, what about the parameter domain? This projects onto, so the domain in u and v is going to be the full disk of radius 4, right? This projects onto, if you look at the xy, onto this disk with radius 4, right? If you project the entire cone on the xy plane. So because u and v are the previous x and y, the parameter domain D will be the full disk. So probably when I compute the surface integral, I'm going to choose eventually polar coordinates for the double integral that is used to compute the surface integral. Okay, so therefore r of uv, the surface in the parametric form, is uv square root of u squared plus v squared. And we're going to need Ru cross Rv, so let's do the partials. Ru is 1, 0, partial u of the radical, that becomes u over square root of u squared plus v squared. And Rv is 0, 1, partial v, which is v over square root of u squared plus v squared. Okay, what about Ru cross Rv? First component will be minus u over square root of u squared plus v squared. Middle component is minus v over that radical. Last component 1 minus 0, which is 1. Now notice what you want in the actual problem, because you want the normal to be oriented downward, you're going to need, in this case, Rv cross Ru, right? The opposite of this. So look at the cone, we want the normal pointed downward, which means the third component should be negative when I set up the surface integral. What else do I need? Well, I need the curl of the vector field. So the curl of f, let's set up again our symbolic determinant for the curl. Components are minus y, x, negative 2. This is going to be quite easy. First component of the curl will be 0, 0 minus 0. middle component partial x of minus 2 minus partial z of negative y, which is 0 again. And then partial x of x is 1 minus partial y of negative 1, which is negative 1. So 1 minus negative 1 is 2. So the curl actually is also easy to integrate. So I mean, you see, it's kind of a wash here. I mean, both integrals are, well, I mean, we'll see. It's slightly more difficult or longer via the surface integral here, the curl, mostly because of the preparation. But the integral won't be terrible either, especially in polar coordinates. So finally, let's set up the surface integral of the curl dot and ds, which turns into a double integral of the curl evaluated at the surface, but there's nothing to plug in into the curl because it ended up being constant, dot rv cross ru, which is u over the square root v over that square root and then negative 1. So that's a double integral which solves the surface integral. So in the end, this also becomes a constant, right? So yeah, I mean, so that's as easy as it gets. The dot product will be actually minus 2 because it's 0 plus 0 minus 2 dA. We're going to do this via polar coordinates because of the shape of the domain, the parameter domain. So in polar coordinates, the bounds are 0 and 2 pi for theta because it's a full disk, and 0 to 4 for the radius, negative 2, and then dA in polar coordinates is r dr d theta. So I mean, I hope you guys appreciate, especially if you took this class, definitely go slower and stop the video to catch up if you need to. Notice how easy it is to go through lots of previous concepts, right? I mean, how you set up polar coordinates, because, you know, to check this theorem, you go through line integral, surface integral, double integral, maybe in Cartesian, polar coordinates. So it's a wonderful review toward the end, which is the reason we just go slow with all the steps. Finally, this splits into a product of two integrals of 1 d theta and then of minus, I can put the minus 2 out, and then of r d theta, r dr. Minus 2 pi r squared over 2 between 0 and 4. That's minus 2 pi 16 over 2, which is 8. So altogether, as expected, minus 32 pi. All right, so this is Stoke's theorem. That's it for today. Next time, we're going to go over the last topic, which is the so-called divergence theorem. See you later.